school. I will start with the first course given by Etienne. So it was initially planned that Etienne Ukraine would give the talk, but unfortunately he couldn't come. So Etienne jumped in and is going to give the talk. And so Etienne is assistant professor in Austin, UT of Austin, and he did his PhD at Columbia with Stephen Winspoon and a postdoc at Harvard. And he'll be talking about Laplace-Beltrami operators and how you can use them for geometry processing.
All right, thanks a lot. Like Klaus was saying, unfortunately, Etienne was supposed to give this talk, but he busted his foot, he had a bike accident, he couldn't make it. So I'm going to give this tutorial for him. And we've already seen several times how the Laplace-Beltrami operator is very useful in geometry processing tasks. We've seen it several times yesterday. We saw it with mappings, we saw it with computing deformations. And this lecture is all going to be about theoretical basis and some information about how to discretize Laplacian in practice. So usually what you do is it's a remarkably common pipeline. You have some right-hand side f, and then you want to solve some kind of system. You want to solve some Laplace u equals f. Then you want to take that u and do something with it. Maybe this u now represents a deformation you want to apply to a mesh. Where this u is, you want to take this and do some post-processing. And it's extremely common for graphics algorithms to be able to be written in this way. And therefore, it's very useful to know how to solve the Laplace-Beltrami operator thoroughly, to really understand it. Because this is kind of a common tool. As soon as you understand how to do this, if you can take a problem and transform it into just a linear system involving the Laplacian, then you know exactly how to do it. You can leverage everything you know about the Laplacian. You can leverage all the theoretical results you know about the Laplacian. And the Laplacian is also remarkably general. If you understand how the Laplacian works in a triangle mesh, it's not so hard to extend it to make it work on tetrahedral meshes, or to make it work on point clouds, or to make it work on all kinds of more general geometry. So the two topics I'm going to cover in this tutorial today, I'm going to talk about the smooth theory of the Laplacian, and I'm going to talk about a bit how to discretize it for triangle meshes. Now, this tutorial we originally prepared, me and Keenan and Justin Solomon, together for SGP 2 years ago. The version 2 years ago was 3 hours long, and if I try to go for 3 hours today, I think I'm going to run into some trouble. So I'll give an abridged version of this today. I'm just going to talk about the theory and about the discretization. There's a third part of the tutorial that you can find online. It also talks about some applications. It kind of overlaps a lot of what you've already seen on previous days, and we'll see again later today. So for that reason, I'm not going to go too much into the applications, but keep in mind there is a third part you can look up online if you want more information. All right, so let's start with the smooth theory. So let's start with the following model problem. Let's say I have some region in the plane, and I give you some function, and I tell you the function values on the boundary. So I have this function f, and I tell you I want f to be -1 along this blue part of the boundary, and I want f to be 1 on this red part of the boundary. And now I want you to fill in f on the inside of the domain. And I want you to fill it in a way that's as smooth as possible. Well, what does this even mean? What does it mean if I say to fill it in as smooth as possible? Now, smooth is a technical term, right? Smooth means it has a bunch of derivatives. But this is not really what we intuitively mean by smooth. If I give you a C infinity function that's super bumpy, that's not what I call smooth. Right? So what do I call smooth? If I have a constant function, I consider that pretty smooth. If I have a linear function, I also consider that pretty smooth. What about more generally? If I say, okay, I'm going to fill this in by just making half of this region blue and half of this region red, even though it's very smooth up here and very smooth down here, there's a huge jump where it goes from red to blue, where it jumps from 1 to -1. I don't call that smooth, even though it looks kind of smooth. It looks nice and cell-shaded, right? What I really want is I want f to be continuous, and I don't want it to vary too much. And how can I measure whether or not f is smooth? Well, I can look at the gradient of f, and I can measure its magnitude. And if the gradient of f has a very large magnitude, then my function is changing very quickly over a very small region of space, and that must mean that I'm not smooth. And if the gradient of f is very low magnitude, that must mean I'm smooth. So what I can do is I can write down an energy, which just looks at the gradient of f and integrates it up over the entire region. And this is called the Dirichlet energy. You've seen this at least 3 times already. Yes, you did. And now what I'm going to say is, this Dirichlet energy measures how smooth my result is. So that's something that looks like this. This is a very splotchy interpolation of the boundary values. This is not a very smooth solution. In fact, if I look at the Dirichlet energy, I can see here that the energy is very high, especially in regions of high splotchiness. If I have a constant function, then this thing is 0. So at least that's a good sign, right? At least I'm going to get 0 if I have something that's constant. It's kind of as smooth as you can get. And if it's not constant, it's always going to be positive. Right? We integrate a positive thing over a region and we get something positive out. Okay, so now I'm just going to say that the solution to my problem of interpolating f is going to be whatever minimizes the Dirichlet energy. How do we find this? Well, you can take a look at the Dirichlet energy. You can do some integration by parts. And if you do some integration by parts, I'm not going to go through the math here. You can show that the Dirichlet energy can be written in this form here as the integral of the function f times this linear operator of the Laplacian applied to f. And now, if you stare at this thing is an integral, right? It's an integral over a region. But if you kind of squinted this and think what would this look like if we were to discretize, this would look something like f transpose times matrix times f. This is kind of infinite dimensional version of f transpose times matrix times f. And if I want to minimize a function that's f transpose times matrix times f, what do I get? Well, when I take the derivative instead of equal to 0, what am I going to get as the derivative of f transpose times matrix times f? Yeah. Yeah, I'm just going to get matrix times f, 2 matrix f, something like this, right? And actually deriving this in the smooth case is much harder than doing it in the finite dimensional case. You have to use high-implicit variations, which I'm not going to go through. But you can show that the gradient of the Dirichlet energy is the Laplacian of f. And this is the definition we're going to use of the Laplacian. Laplacian is the gradient of the Dirichlet energy, or the negative gradient of the Dirichlet energy. So the Laplacian is going to tell you how you have to change some initial function if you pick the interpolation problem in a way that you approach as quickly as possible to the smooth solution. So for example, here I've plotted some initial very bad solution to the interpolation problem. And here I've plotted the Laplacian of f. And you can see that if I wanted to make this smoother, right? I have these regions, like over here, I have this red island. I want to make that island bluer. And you can see that if you look at the corresponding place down here, this is trying to make that region bluer. And similarly over here, I have this island with blue, I want to make that region redder, and this Laplacian is telling me to make that region red. So this Laplacian is telling me what the gradient is. And this is kind of a funny gradient. I usually think of gradient with respect to one variable, gradient with respect to a few variables. This is a gradient with respect to a function. So it's a gradient with respect to infinitely many variables. But it still makes sense in the direction of steepest descent, right? This is the direction where we move f in to make it smooth. Does that make sense? Okay. So now if I want to find a solution to my interpolation problem, I want to find where the gradient is equal to 0. That means I'm at a critical point. Right? So I want to set, if I have a function and Laplacian of f equals 0, that means that it satisfies, it minimizes the Dirichlet energy. And if I do that for my region, I get something that looks like this. And this, I gotta say, looks pretty darn smooth. If I want to find this, I can write down a PDE, which tells me that the function f satisfies this condition. So the Laplacian of f has to be 0 everywhere inside the region. And I also have to say that f is fixed at the boundary. F has to satisfy the conditions I prescribed on the boundary. Why do I need this? What would happen if I didn't have this condition here on the boundary? What would I get for my smoothest f? Yeah, I can just make it constant, right? I can just set f equal to 0, or f equal to 1, right? Now I have a constant function. That's Dirichlet energy 0. That's as smooth as I can get. It's the fact that I have these boundary conditions that makes it so that the Dirichlet energy can't go to 0. It's stuck. It can decrease to a point, and when we get this nice smooth solution, it can't get any smaller. Now, this equation here is Laplace's equation. It's probably the most famous PDE you'll ever find. And it has a physical meaning, has many physical meanings. It's related to diffusion, it's related to all kinds of smoothing processes. Probably most famous is related to heat. This is the equation for heat flow at steady state. So if I imagine that this red and blue function I'm prescribing the boundary is really a temperature. So I'm setting the temperature of this boundary here to be -1 degree. And I'm setting the temperature of this boundary to be 1 degree. And I let the heat just flow and wait infinitely long. Eventually the temperature is going to settle to some value on my region, and the solution to the Laplace equation tells me what the temperature is everywhere inside. Now, if I can do this for a region in the plane, I can also do this for a bunny in space. So now I've got a bunny, and I'm prescribing f at some points on the bunny. I'm saying f has to be -1 on the ears of the bunny and 1 on the tail of the bunny. And now I want to know, how do I interpolate f smoothly over the bunny? Here's a bad example. Here's an f that's very splotchy. Right? How do I do it? How do I take what we just did in the plane and apply it to the bunny? What are the steps? How can I look at this function and decide it's not smooth? Yeah? Yeah, well, just like I can define the Dirichlet energy in the plane, I can define Dirichlet energy on the bunny, right? I can look at a point on the bunny and say, how quickly is the function changing at that point? I'm looking at the neighbors, right? As long as I can take the gradient of my function, and if I zoom in on the bunny looks planar, right? It's a manifold, so I can take the gradient of the function on the bunny. And I can measure the magnitude, and I can integrate that up into the bunny. So I can still define a Dirichlet energy on the bunny, which measures how smooth this solution is. And I can plot that. You can see that this is very large values in this Dirichlet energy, right? This is a very non-smooth solution. And now I can do the same thing. I can say, I have this energy, which tells me how good of a solution this is. I'm going to take the gradient of that, and I'm going to call that my Laplacian. And if the gradient's equal to 0, then I'm the smoothest I can get. I'm at the minimum of my Dirichlet energy. And if you do that, I get this. I get this as the interpolation of the bunny function. And this is now just a Laplacian applied to the bunny mesh. When you're applied to the bunny, so the plane you call the Laplace-Beltrami operator does exactly the same thing. It's just the gradient of the Dirichlet energy. Is that clear to everyone? And now, if you have some other setting, if you have high dimensions, if you want to do this, instead of interpolating on a surface, if you want to interpolate on a volume, or if you just have a point cloud, if you have some other crazy kind of data, and you want to do interpolation on it, as long as you can define a Dirichlet energy, as long as you can take a gradient and measure its magnitude and integrate that up, then you can define a Laplacian, and then you can solve the heat equation. So this is a very, very general recipe. Today we're going to talk about the smooth case and triangle meshes, but the really key thing here is how general this recipe is. As long as you can define this energy, you can define a Laplacian. And the heat equation is one of the most robust PDEs you'll find as well. It works under all kinds of crazy situations. If you have a fractal, if you have the Cox snowflake, and you try to do the heat equation on that, you'll still get a solution. And you can prove that under very, very general conditions, there's a unique solution to the heat equation. And this really shouldn't be too surprising because of the physical interpretation, right? If you give me some crazy shape, and you give me some temperatures on the outside, then just imagine this is a sheet of metal and applying heat to the boundary. Nature is going to do something, right? The temperature is going to do something if I wait long enough. It's going to reach some steady state. So there must be a solution to the heat equation, right? But you can actually prove this formally that there is a solution to the heat equation no matter how crazy the shape is, and in particular it still works if you have discrete surfaces. So if your boundary is not smooth, but just piecewise smooth, for example, if you have a triangle mesh with a piecewise linear, then a solution also exists. There's no problem. All right, so we have this energy that we want to minimize, the Dirichlet energy. And there was a nice talk yesterday about optimization methods. If I have some function I want to minimize it, what can I do? Well, the simplest possible thing I can do is gradient descent. You guys remember gradient descent? How does it work? What's that? Who wants to tell me how it works? Yeah?
You walk down the gradient a little bit, calculate a new gradient, then you do it again and repeat until you find a minimum.
That's right. So I calculate the gradient, and I take a step in that direction. And then I calculate the gradient again, and I take another step, and I keep going until I reach the minimum. Right? Each time the gradient is telling me the direction. I guess I want to take the negative gradient, right? I want the direction of steepest descent. Well, if I want to apply gradient descent to the Dirichlet energy, what do I do? What's the gradient of the Dirichlet energy? That's right. So I calculate Laplace f. I take a step in Laplace f direction. I calculate Laplace again. I take a step again. And if I write this as a differential equation, if I imagine my steps are getting smaller and smaller and smaller, right? Each time I'm taking a step, I'm taking a step in the Laplace f direction, right? And so this, if I imagine I'm shrinking my steps, so I get a smooth path. My descent is not step, 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 but a smooth walk towards the minimum. The direction I'm going to be walking is going to be solved by this differential equation. And this tells you how heat evolves over a surface. So instead of looking at the heat at steady state, right? So the heat equation we had before said here are the boundary temperatures. If you wait infinitely long, where are the temperatures going to be on the inside? If I now have this ODE here, what it's doing is it's taking some initial temperature to tell you how's that temperature changing over time as it's approaching the steady state. And you can see what happens if I try to solve this on the bunny. So I have some initial splotchy distribution of temperatures on the bunny. And as I wait, as time increases, the temperature evens out. And my Dirichlet energy is decreasing. If I look here, you can see the Dirichlet energy is getting smaller and smaller as time goes on. What's going to happen if I wait infinitely long? What's my Dirichlet energy going to be? Well, yeah, so now it depends on my boundary conditions, right? If I have no conditions on my heat, if my heat's allowed to redistribute however it wants, then it will be zero. I'm going to get a constant temperature everywhere on my body. The Dirichlet energy of the constant is zero. If I do a thing like before, where I set the ears to have to be -1 hot and the tail to be 1 hot, then I'm going to converge to something that doesn't have zero Dirichlet energy. It has some limited Dirichlet energy. But in either case, the temperature at time infinity is going to have a Laplacian equal to 0. That's where I reach my minimum. Okay, so we can modify this setup a bit. So let's go back to this domain. I'm still going to prescribe f to be 1 down here and -1 up here, but now I'm going to do something different along this boundary here. Instead of prescribing the value of f on this boundary, I'm going to say that f, the derivative of f, in the boundary normal direction is going to have to equal to 0. So I basically cut my boundary into 2 regions. I have the original boundary conditions here where the f is prescribed. And then here the gradient of f dot n just tells you what is the component of the gradient of f in the normal direction. I'm going to set that equal to some second function, g, here in this case is 0. This 0 here is kind of the most common kind of condition you'll impose. It's called the natural boundary conditions. And what's the physical interpretation here? The physical interpretation is that temperature is not allowed to escape anywhere along this boundary. So the temperature is fixed here, the temperature is fixed there, and the temperature can't flow outside this boundary. So this would correspond, for example, to taking this, imagine this is a metal plate up in space, and I'm applying some heat to one end and some cold to the other end, and the temperature can't escape into space along the rest of the boundary. And what you'll get if you do this, you'll get that the function is a gradient from the hot end to the cold. And these are called Neumann boundary conditions. This is kind of the second most common kind of boundary conditions after Dirichlet boundary conditions, the conditions where you actually set the temperature of it. So because you can use the Laplacian to do smoothing, interpolation using the Laplacian has been used all over the place in practice. You can use to deform characters, right? You basically prescribe positions for 2 points in the character, then you interpolate the deformation throughout the rest of the character. And that gives you the shape of the character everywhere else. You can also use it for things like editing surfaces. You can take a camera and you want to remove the hump, right? So you delete the hump, but you don't want to just slice off the hump. You're going to get discontinuities when you sliced, right? And so by smoothly interpolating the change to the hump, you're going to get a smooth panel looks a lot better. We can keep modifying things. I can take my region. I can set f to be -1 on the boundary, but now I'm also going to apply a hot plate in the middle. So I'm imagining I'm taking a blowtorch, I'm taking a hot plate, and I'm constantly adding more temperature to the middle. So what's going to happen? I'm inserting temperature in the middle, and the temperature is going to flow towards the boundary. So I basically have a heat source in the middle and a heat sink on the boundary, so the temperature is going to flow from the inside to the boundary. If I write this as a differential equation, I have that the change in the temperature at every point now is not just the Laplacian. The Laplacian would just be if the temperature were to flow naturally. But I'm also injecting extra temperature, it's g of x. So g of x in this case is 1 on this region here, and it's 0 everywhere else on the inside. What do I get at steady state? What do I get at time infinity if I flow using this differential equation? So what is this doing? This differential equation is taking some initial temperature, and the temperature is changing, right? This is doing gradient descent, right? This is doing evolving the temperature over time. So the heat's going to redistribute, until eventually, at time infinity, the temperature is not going to be changing anymore. And when the temperature is not changing anymore, what's going to be true about the temperature? What's the equation's going to be satisfied? Yeah.
Minus the plus f is g.
Minus the plus f is g. Why do you get that?
Because the time the FDT is 0, it's not changing anymore.
That's right. Once you're at steady state, the FDT is 0. Right? Once the heat's redistributed itself to the point where it's not changing anymore, the FDT is 0. And that means the right-hand side has to be 0. And if you want to directly solve for this without solving the ODE, if you don't want to actually do this gradient descent, you just want to solve for it, just like with the Laplace equation before, we just have to solve the cos x minus g. And of course, we also have to put back in our boundary conditions that f is equal to minus 1 with that. We get something that looks like this. The only difference between this equation and the Laplace equation is that there's a right-hand side. There's a g over here, where there used to be a 0. And if you stick in a g instead of a 0, this is called Poisson's equation. This equation arises a lot because just like the Laplace equation comes from trying to minimize the Dirichlet energy, the Poisson equation also comes from minimizing the energy. If you take the Dirichlet energy and you stick in an extra v in here, right? So imagine v is a vector field on your domain. And you're saying that you want grad f to be as close as possible to v on the domain. If you try to minimize this, you'll get exactly this Poisson's equation where the g is played by a divergence of v. So this kind of objective function arises a lot in graphical application, and every time it does, you end up getting a Poisson equation. It's almost exactly the same as the Poisson equation. This is a g. Okay, so Laplacian has some important algebraic properties I want to go through real quickly. First of all, it's a linear operator. So if I take the Laplace of the sum of two functions, it's the same as taking the sum of the Laplace of two functions. Same thing with scaling. If I multiply a function by a constant, then it's just constant times the Laplacian of the function. If I have a constant function, the Laplacian is equal to 0. There's several properties that are true if you look at the product of the function and the Laplacian of the function. So if I have two functions, f and g, and I have some region, let's say I have a region that has no boundary, where f and g vanish from the boundary. Then by integration by parts, you can actually show it doesn't matter which order you have the f and the g here. You can either do f times Laplace g or g times Laplace f, and you get the same thing. And the reason for this is that you can integrate by parts, and yeah, if you integrate either one by parts, you end up getting the same kind of Dirichlet type expression. If f and g are equal, then you just get the Dirichlet energy. If f and g are not equal, then you just get this inner product of two gradients. It doesn't matter which order I take the inner product of these two gradients. The other property that's related to this is if I integrate up f times Laplace f, I'm always going to get something negative. Why is that? Yeah, that's right. If I just look at this equation above, right, f and g are equal, then I get that this integral is equal to negative the Dirichlet energy, right? And the Dirichlet energy is always positive, or at least non-negative. So this thing always has to be non-positive. And these equations, if you look at them, this looks a lot like the Laplacian is an infinite dimensional negative semi-definite matrix, right? If you have a negative semi-definite matrix, then f transpose matrix f is always less than or equal to 0 for any one. Right. What does this equation here correspond to? Well, this equation corresponds to symmetry of the matrix. Right? If f transpose Laplace g is equal to g transpose Laplace f, that means that the matrix is symmetric. And this equation just means that there's a true kernel to the matrix. If you plug in a constant, you get 0. So this intuition is very useful. Of course, this is not rigorous, right? This is not a rigorous statement. But it's intuitively true that you can think of the Laplacian as a generalization of a negative semi-definite matrix, just that's infinitely big. And this is very useful because it's very useful for thinking about things like the spectrum and so forth, which we're going to talk about later. Because the properties are very, very similar to a negative semi-definite matrix. A couple of extra properties. Maybe you've seen this formula before. The Laplacian is equal to the divergence of the gradient. I don't like this formula that much because in order to use this formula, you have to know how to write down the divergence, which is not so obvious on things like bunnies. In the plane, there's formulas for divergence, and you can come up with formulas for divergence on manifolds, on bunnies. If you look at discrete exterior calculus is a field of computer graphics. It's all about how to write down things like divergence in the principal way. But you don't really need this for the Laplacian. All you need for the Laplacian is a way to write down the Dirichlet energy. And then you just take the gradient and that's the Laplacian. This formula is still too useful, and I've had somewhere on this slides, because people do use this all the time. Finally, if you're an Rn, then there's a very, very simple formulas for the Laplacian. Laplacian is just the sum of the second derivatives of the function. So in 1D, the Laplacian is just the second derivative. And that should make sense. If you have a one-dimensional function, how wiggly is that function? Well, that's just measured by the second derivative, right? If you're an Rn, there's actually a very easy way to solve the Poisson equation. And the way to do this is to use Green's function. So what's Green's function? Let's say I want to solve the Poisson equation for one very special right-hand side g. I want g to be 0 everywhere, except for at one point. Now, at one point, I want g to be the Dirac delta. I want it to be an infinite spike at one point. It turns out that if you have this g, you can come up with an explicit answer to Poisson's equation. It looks something like this. And this is called the Green's function. If I take the Laplacian of this thing here, I'm going to get that it's 0 everywhere except in the middle here, where it diverges to infinity. And I get a Dirac delta. Now, why is it useful to have this particular right-hand side? Probably in practice, you're never going to have g being a Dirac delta at some point. This is not kind of a practical right-hand side. But the reason this is useful is to make this extend to arbitrary g. So let's say I, instead of a single spike, I had some finite set of spikes in the plane. So I had a finite set of Dirac deltas in the plane. And I wanted to solve the Poisson equation with that right-hand side. How do I do it? Let's say I have a spike here and also a spike over here. So I've got two spikes, and I want to solve Laplace f equals those two spikes. How do I do it? Yeah, I just take this solution, I translate it. So now I've got this solution here, I've got a translated version of this solution, I add them together, and I claim this is the solution of the Poisson equation with two spikes. Why is this? Well, because Laplace is linear, right? So I take the Laplacian of the first version of the spike, I get 0 everywhere except the delta there. I take the Laplacian of the second version, I get 0 everywhere except the delta here, and so the result is just the two deltas. Does that make sense? Okay, so now I can easily write down the solution for any finite set of deltas scattered around in the plane. This is still not so useful, but the trick now is I can actually take an infinite set of Dirac deltas. If I have an infinite set of Dirac deltas, and I basically take my fundamental solution, my Green's function, I just copy it once for every one of the infinitely many points in the plane where I have a Dirac delta. I can get the solution to the Poisson equation from any right-hand side. This turns into a convolution. So if you give me some g, which is some regular function, that doesn't have any Dirac deltas in it, just any old function that you want to use, the right-hand side, you can convolve this fundamental solution. Basically, it corresponds to taking this and smearing it out, copying it all over the plane. You're going to get a solution to the Poisson equation for this right-hand side. Now, the problem with this is that this only really works in Rn. If you want to do this on the bunny, you're going to be out of luck, because you're not going to be able to find this Green's function on the bunny. But if you want to solve this in Rn, then this trick is extremely useful. You can just write down very easy expressions for the answer to this Poisson equation. If you have a function whose Laplacian is 0, this is called a harmonic function. And harmonic functions have all kinds of nice properties. We already know that these functions are as smooth as possible in some sense, right? If you have a harmonic function and you look at the boundary, and you don't let the boundary change, but you're allowed to change the insides, it's impossible to make the function any smoother than it already is. Because this function is already minimizing the Dirichlet energy. Right? It's already a solution to the gradient of Dirichlet energy equals to 0. In fact, it's not only smooth in an intuitive sense, but it's also smooth in a rigorous sense. All the derivatives of this thing exist, and it's also analytic. So you can compute the Taylor series of this thing on the inside. On the boundary, things can go nuts. Right? Here, for example, is a function I get if I set the function to be 1 on half the circle and -1 on the other half of the circle. So you got on the boundary, you got this huge jump where the boundary value goes from -1 to 1. Then the inside's going to try as hard as possible to smooth that out. So this function is going to be smooth and analytic everywhere on the inside, even though the boundary is a jump. Another important property of harmonic functions is that if you take a point on a harmonic function and you look at a neighborhood, you basically take a ball around this point and you average the value around this point, you're going to get the same value on the inside. This is not just true in the limit, right? If you have any continuous function, if you look close enough, you're going to get that the middle point is the same as its neighbors, right? This is true no matter how big you make the neighborhood. So you can take this huge disk over here and average the value of the harmonic function everywhere over this disk. You're going to get that the average is equal to the value of the mean. This property carries over to discrete harmonic functions. If you saw the first lecture yesterday about Tut embeddings, the Tut embedding made use of the fact that if you have a harmonic function, that the middle vertex is the average of its neighbors. Another important property of harmonic functions is the maximum principle. If you have a harmonic function, there can't be any maximum or minimum of this function except on the boundaries. So you saw that here in these pictures, right? Even though you have these crazy boundaries that oscillate a lot, all the maximum and minimum of this function are on the boundary. They're none on the inside. There can't be solid points on the inside. There can't be any maximum or minimum. This kind of makes sense. If there were a maximum on the inside, you could smooth the function out by flattening the maximum. Right? Same thing with the minimum. You can smooth it out by getting rid of it. All right. So, more geometric properties of the Laplacian. Let's say you have a curve in the plane. So I have some parametric curve. So I can think of this curve as some function x and some function y that depend on some parameter. If I want to calculate the arc length of this curve, what's the arc length equal to? Well, it's just equal to the sum of the gradient of the x plus the sum of plus the gradient of the y. Right? This is going to measure the arc length of the curve. Maybe even off by a factor of a half. And what is this? This is just the Dirichlet energy of the x function plus the Dirichlet energy of the y function. Right? So if I have a curve that minimizes arc length, what's going to be true about the curve?
Minimizes or even boundary equation.
Yeah, that's right. So I take some curve and I fix 2 points, and I want to minimize the arc length. What am I going to get?
Straight line.
That's right. You're going to get a straight line. That's kind of classic Euclidean geometry theorem, right? And you can see, you can even prove this is true using the properties of Laplacian, because if you have a minimizer of the arc length, right, that means that the gradient with respect to x has to be 0, and the gradient with respect to y has to be 0. It means that the Laplacian of x has to be 0, and the Laplacian of y has to be 0. And if you have a 1D harmonic function, it has to just be a straight line. So if you take the Laplacian of the curve, and here I'm abusing notation. So this curve here, I'm thinking of as being actually 2 coordinates, an x coordinate and a y coordinate. And when I say take the Laplacian of this curve, I'm saying take the Laplacian of the x coordinate and the Laplacian of the y coordinate and treat that as a vector. This is the gradient of the arc length. And intuitively, this is related to the curvature of the curve. If I look at this curve here, and I want to decrease the arc length as much as possible at a point, what I want to do is, at highly curved regions, I want to move the curve large distances. And at zero curved regions, I want to change the curve at all. So you can do the calculus and derive if this is true, but intuitively it should also be clear that if you have a curve, you want to minimize the arc length as fast as possible. What you want to do is you want to flatten the curve where you have bumps. You want to take highly curved regions and make them flat. And flowing the curve in the Laplacian direction does this. Laplacian tells you the gradient of the arc. Now, in a curve, this is not so useful because it's very obvious what the shortest curve should be between 2 points. It should just be a straight line. But now you can do the same thing in higher dimensions. So now let's say you have a surface. You can think of the surface as being parametrized by 2 numbers, s and t, and being made up of 3 functions, which tell you the x, y, and z coordinate of the surface in space. And you can do the same thing as before. If you take the Dirichlet energy of the x and the y and z coordinates and sum them up, that gives you the surface area of the surface. And then the Laplacian of the Dirichlet energy tells you what is the gradient of the surface area. And this turns out to be the mean curvature norm. So the Laplacian of a surface is just the normal to the surface times the mean curvature. And if you have a surface that's minimum surface area, that means that the surface area is a critical, the surface is a critical point of the surface area. That means that this has to be 0. That means that the mean curvature has to be 0. So if a surface has minimal surface area, it's called a minimal surface, it has mean curvature 0, and in 1D you can't get very interesting minimal curves. If you fix 2 points and you say find the shortest curve between, you always get a straight line. But for surfaces, you get much more interesting shapes. If I say, find a surface that goes through these 3 rings, it has minimum surface area, you get these soap type surfaces. And these are the minimal surfaces. These are the harmonic surfaces, the surfaces that have mean curvature 0. Okay, other geometric properties. The Laplacian is intrinsic. What do I mean by intrinsic? I mean that if I have some region and I calculate the Laplacian on this, I get the same answer if I rotate the region. This should be pretty intuitive. Why is it true that it doesn't matter? Why can't I just rotate the region and the Laplacian stays unchanged? Yeah.
Because of the physics, if I have a plate and I want to rotate a plate, it should give the same result.
Yeah, that's right. So at least intuitively from the physics, it shouldn't matter how I rotate my plate. The heat's going to flow the same way on the plate, right? The Dirichlet energy also doesn't really care how you orient this thing, right? If I take a function on the plate and I rotate the function and the plate, I'm going to get the same gradient magnitudes. Right? I'm going to get the same Dirichlet energy, so I'm going to get the same Laplacian. Same thing if I take my plate and I roll it up. So this is maybe very obvious. This is maybe less obvious. I can just take this plate and I roll it up. And if I now calculate heat flow in the rolled up plate, I'm going to get the exact same thing as on the flattened plate. For the exact same reason, right? Physics doesn't care what this thing looks like when it's embedded in 3D. All it really cares about is the Dirichlet energy, which only cares about what this thing looks like intrinsically. All right. The last thing I want to mention about the theory of the Laplacian is that it's very related to signal processing, to the Fourier transform. So let's say we have a cosine of I times x, where I is some integer. As I change i's, I make I higher integer, I get more and more high frequency oscillations, right? The cosine becomes more and more high frequency. And these are the Fourier bases for a 1D signal. If you assume that the signal has to be 0 at 0 and 2 pi, right? So I assume I have some periodic signal at 0 and 2 pi. And I can always express that as a sum of a bunch of these cosines. And these cosines, yeah, so I can always express any function that satisfies these previous conditions as a sum of these cosines. And these cosines are also harmonic functions. Oh no, sorry, they're eigenfunctions of the Laplacian. So if I take one of these functions, I take the Laplacian. So the Laplacian in 1D is just the second derivative. So I'm taking the second derivative of cosine of ix. I'm just going to get negative I squared times cosine of ix. Right? Okay, that means that the Dirichlet energy of f also is just I squared times, so the Dirichlet energy for these is just I squared. And so if I have some function f and I express it as a sum of a bunch of these cosines, this Dirichlet energy, I can calculate, if I know the coefficients of this expansion, I can just calculate as a sum of I squared times the coefficients. The reason for this is if I take phi times Laplacian of phi, that's going to be the same as the negative of the Dirichlet energy, right? And if these things are normalized appropriately, I'm just going to get I squared. So what is this saying? This is saying that if I know the expansion of my function in this basis, the terms of this basis that have small I, those correspond to low frequency parts of my function. Those correspond to parts of my function that have small Dirichlet energy. Those are the smooth parts of my function. And if I look at the parts of this expansion that have high I, those correspond to the high frequency detail of my function. So in signal processing, a lot of the times what you want to do is you want to throw away, for example, the parts that have high frequency. Just keep the low frequency part of the signal. You want to denoise a signal, for example, right? You do a low pass filter, so you get rid of all the high frequencies. Right? What you're doing is you're getting rid of all the parts that contribute the most to the Dirichlet energy and keeping the parts that contribute the least. Now we can do exactly the same thing on a bunny, or in higher dimensions, or in any other setting where you can define the Laplacian. So in any setting beyond 1D, I can also define an eigenfunction of the Laplacian. By this I mean a function where if I take the Laplacian, I get some constant times that function back out. Right? Thinking again of this Laplacian just like if it's a matrix. Right? If I have a matrix, an eigenfunction of the matrix is just a vector that you multiply the matrix by, and then you get the same vector out 5 times. The only extra detail here is you have to set some boundary conditions. I'm just going to assume that the function is 0 everywhere on the boundary. And I'm just going to normalize this function so that it's, right? You can always normalize your eigenvectors. It doesn't change anything. Now, if I have a finite dimensional negative semi-definite matrix, all of my eigenvalues are going to be negative. Right? That's kind of the definition of a negative semi-definite matrix. I'm going to have one or more eigenvalues that are 0, and all the others are going to be negative. And it turns out that intuition also carries over to the Laplacian. You can show that if you have a Laplacian, then you have 1, 0 eigenvalue. What's the eigenvector that corresponds to the 0 eigenvalue? What's a function f for the Laplacian of f equals 0 times f?
Zero function, constant.
Yeah, yeah, exactly. If I'm constant, right? I'm taking the Laplacian of the constant. I'm just going to get 0. Right? So the constant function is the one that's 0 eigenvalue. Then all the other eigenvalues are all going to be negative. And you can calculate these things, right? So if you're you can calculate these things. If I take a bunny surface and I look at the eigenfunctions, I'm not going to show the first eigenfunction. The first eigenfunction is boring, it's just a constant. But if I look at the others, and I plot these, so here I've plotted the positive region is red, the negative region is blue. You can see here a few of the eigenfunctions of the bunny. You can see they actually show a lot of symmetry. They actually reveal a lot about the bunny. The first eigenfunction is just a gradient. This should make sense. The first eigenfunctions have very low Dirichlet energy, and you can't get much lower than just a linear gradient. As the eigenfunction becomes higher and higher, you get more and more details. And you can see that the eigenfunctions kind of conform to the geometry of the bunny. You can see that this eigenfunction here is picking out the ears of the bunny. There have been several papers and graphics that use the spectrum of the Laplacian as eigenfunctions to try to identify symmetries or to identify segments of the object. And as you keep going up, as you keep increasing the eigenvalue, the eigenfunctions become more and more high frequency. You get more and more changes of sign. So here you only had one change of sign around the middle of the bunny. We're picking negative positive. And here you have lots of regions with sign changes. And if you have any function on the bunny, you can express that function as a sum of a bunch of these eigenfunctions. Just like you express a function of the 1D segment as a bunch of cosines. And the reason you want to do this is because you have the splitting of the Dirichlet energy just like before. If you have a function expressed in this way, the Dirichlet energy of this function here is just it's just a sum of the coefficients times the eigenvalues. And so if you have that this function has large coefficients for the low frequency eigenfunctions and small coefficients for the large frequency eigenfunctions, then you have a very smooth function. If the opposite is true, then you have a very noisy function. And so you can do signal processing. You can, for example, take a function and throw out all the terms that correspond to high frequency eigenfunctions. You're going to get a smoother version of your function on the bunny. Here, for example, is what happens if you take the bunny. So if I treat the bunny as a function on itself, right? So I treat the bunny as an x function, a y function, and a z function on the bunny itself. And I throw away all the high frequencies, and I get a very smooth version of the bunny. This is kind of a bunny where, if you take a sucker and you suck on it for a while, and you pull it out, and it's all very, very smooth out. Right? This is kind of what's happened to the bunny here. As I keep adding more and more modes, I throw out fewer and fewer of the modes, I get something that is closer and closer to the original. So that's the key point here. If you have some surface, or you have some volume, or you have some generalized region, and you want to do Fourier analysis, you want to do signal processing, all you have to do is you have to take everything you know about signal processing from 1D, and just replace the Fourier basis, the cosines and sines, with the eigenfunctions of the Laplacian. And all what you know about signal processing is going to carry you. And maybe you're already familiar with this. Maybe you already know that if you want to do signal processing on the sphere, you have to use the spherical harmonics. And the spherical harmonics are just the eigenfunctions of the Laplacian for the special case of the sphere. And as long as you can compute the Laplacian, compute its eigenfunctions, you can generalize this thing. Okay, so before I move on to talking about the discrete Laplacian, are there any questions about the smooth stuff? Yeah?
You showed that intrinsic property of the Laplacian.
Did I miss it? All right.
Yeah.
This one.
Yeah, this one. Next one. Yeah. So does that mean that the Laplacian can be used for non-rigid shape matching kind of application?
Yeah. So it's true that if you have two surfaces that are isometrically deformed, right? So you have my body, for example, right? If I move my body around, I'm deforming nearly isometrically, right? And that means that if I calculate the Laplacian on my body in different poses, I'm going to get something that's very, very close. It's not going to be exact, because I'm kind of deforming my muscle the same way, right? But this is absolutely used for shape matching. In fact, if you know about functional maps, the basic idea of functional maps is you can take the spectrum on one surface, and you can map the spectrum to one, you can find correspondences between the spectrum of one surface and another surface. And if you have two surfaces that are nearly isometrically deformed, those are going to match up, right? And they're going to let you find correspondences of points. So yeah, so absolutely, people take advantage of the fact that the isometric deformations of the surface, then the spectrum is the same.
But it cannot be used for non-isometric.
No, it can't. As soon as you have non-isometric deformations, then you no longer have the same intrinsic surface, right? If I take a sheet of metal and I stretch it, right, it's no longer true that heat's going to flow the same on the stretched surface as on the original. Although if it's nearly isometric, then usually things work out okay. Other questions?
Can I ask one more?
Yeah, sure.
So you talk about the matching and correspondence, right? To me, it looks like a global property, not much local. Suppose if I want to get into the figure and aspects of figure rather than a hand, is it still possible to go down to a very local level with Laplacian?
So wait, so can you repeat that? I didn't quite hear.
It seems to be more like a global property, not like a local property. For example, the deformation that you talked about, is it possible to go to the figure level of deformation?
Okay, so the question is, it seems like the eigenfunctions are a local property of the surface. It's possible to go local. The answer is no, not really. If I calculate the Laplacian spectrum on my body, right, the first eigenfunction is going to look something like a gradient. It's going to be highest in my head, it's going to decrease to my feet. This is totally different than if I calculate the first eigenfunction of my arm, which kind of looks like a gradient on my arm. Right? The gradient on my arm looks nothing like the gradient on my whole body. So figuring out how to do partial matching is kind of one of the big unsolved problems related to functional maps. There are some relationships between the two, between a partial surface and a whole surface. If you look at this, the eigenfunctions of the two, there's no obvious relationship. It's not that the eigenfunctions of the arm are a subset of the eigenfunctions of the whole body or anything like that. So unfortunately, no. There's no nice local version of this. Other questions?
Maybe one more.
All right, last one.
So that spectrum that you talked about in that Bunny model, right? So it depends on the mesh size. I mean, the large mesh size is easily computable. So the mesh size is very large.
Yeah.
So the computation of Laplacian easier.
Okay, so if I take the bunny and I scale it, what does that do to my eigenvalues? It's a good question. What happens if I scale it? What does that do to the eigenvalues?
So it's a scale up the values, right? I don't see much difference in the, I mean, the matrix will be scaled, right? So it's not exactly it's going to be the same eigenvalues. The ratios of the values will remain the same.
The ratios are going to be the same, but the scale is going to change, right? One way to think about this, right? If I take, let's say I have some eigenfunction f. So I have a Laplace f equals lambda f. So f Laplace f, assuming that f is normalized, is just going to give me lambda, right? And this is the negative of the Dirichlet energy of f. Dirichlet is just going to scale, right? So I'm going to be integrating over a larger region, right? And that means that my lambda is also going to scale. So if I scale up a surface, it's just going to scale up all the eigenvalues. The functions themselves won't change. The eigenvalues won't change. So yeah, so there's not much, I mean, maybe for numerical reasons, when you actually want to compute this, it helps to scale it so that the, for example, the bunny fits inside a unit sphere or something like that. But mathematically, there's not much advantage to scaling the mesh. All it really does is scale up the eigenvalues.
Then my question was more to do with numerical computation. Is it easy to compute numerically? Stability-wise, is it really stable?
It's not good to have very large numbers in numerical calculations, right? So certainly rescaling the mesh to fit a unit sphere is not a bad idea. It doesn't turn out to usually be a big deal either. We'll talk more about the numerical stuff about doing the same. All right, so you're banned from asking more questions. Any other questions? Yeah.
Do we know how the gradient from the first derivative function, how it will orient itself compared to the shapes?
Yeah, probably. I don't know offhand what the result is there, but somehow it's going to orient itself to the diameter of the shape, the greatest diameter of the shape. Right? If you have an ellipse, right, then it's going to orient itself so that it's a gradient along the long axis of the ellipse. And I think you can prove similar things if you have a more general shape. If you look at the diameter of the shape and look at the longest diameter, it's going to tend to orient itself that way. But I don't know the formal statement for how it orients itself. I do know that it always has just a single zero level sum to it. That it always is a gradient, looks like a gradient. Other questions? All right, so let me move on to the discretization half of the talk. So we're now going to talk about how to compute things like the Laplacian or the Laplacian eigenfunctions in practice on a triangle mesh. I guess before I start, I want to mention I'm going to assume that the triangle mesh is manifold. What this means is I've got a triangle mesh and it's connected up in a way that every edge has two triangles touching it. You don't have fins with more than two triangles touching. And so that if you look at every vertex and look around that vertex, it looks like a fan. You don't have some of these crazy things where it wraps twice around, or you don't have things where there's holes where you try to go into those gaps. You can basically keep walking around the neighborhood of a vertex and come back to where you started and get a triangle fan. Right, this is what I just talked about. It's not really necessary to assume this. You can generalize this stuff to more general meshes if you really want to. This is just going to make all the formulas much easier. So we're just going to assume this. And if you download any mesh, actually that's a lie. If you download a mesh from the internet, it's going to be terrible quality. It's going to be a triangle soup. It's going to have disconnected components just kind of sitting next to each other. But if you download a mesh from a computational geometry data set, it's going to be nice and cleaned up, and it's going to be good. So perhaps you don't need to worry too much about this. If you do want to worry about it, like for example, you might have a mesh that has a boundary. And if you have a boundary to your mesh, then it's no longer true that if you walk around neighboring triangles of a vertex, it closes back up. Right now, you're going to have a gap. And it doesn't really change the formula as much. It changes the formulas a little bit. We're just going to ignore that for today. Just keep this. So maybe you guys know, if you have a triangle mesh, you know, calculate the Laplacian in the mesh. It's a super famous formula for how to do it called the cotan formula. So what you do is you have a triangle mesh. Now you imagine that you've assigned a function valued at every vertex of the mesh. So a discrete function on a surface now is just a single number per vertex of the mesh. And the Laplacian is just going to give you out a new function. So it's going to give you a new value at every vertex of the mesh. And the formula for computing this, you have a vertex I, and you have a function u, which is defined on all the vertices. And you want to calculate the Laplacian of u at a vertex I. You have this nice formula here, called the cotan formula, because all the cotans that appear. The ni down here is the set of all neighbors. So you're going to loop over all the neighbors of this vertex I. You're going to compute the difference between ui and uj. So the value of u here minus the value of u here. You're also going to compute these angles, alpha and beta, that appear in the cotan formula there. And the last thing you need is this a that appears out front. And this a is the area of the vertex. So it's the area of the mesh that belongs to this vertex. It's the area in dark blue that's drawn here. And it's kind of a subtle point of how to compute this thing. There's several different approaches. The simplest thing to do is just to take the area of each of the triangles and just take a third and assign a third of the area to the vertex I. many different ways to derive this thing. If you take a class on finite elements and you look at blur confined elements and how to calculate Laplacian using that, you're going to get this formula. If you look at finite volumes in fluids, for example, you're going to get this formula. It shows up all over the place. Discrete exterior calculus, which I mentioned before, is one way of deriving things like divergence, and from that you're going to get out this exact same formula. And there's a long history of people basically re-deriving these formulas. If you look at the papers in graphics, everyone cites one paper by Conrad and Ulrich Pinkholm. But they were not the first to come up with it. People have been coming up with this forever, even going back to things like the Manhattan Project. And you can look at all these people exact same formula. And actually, there's a very interesting reference. You look at this paper from 1949. This is way before people were actually doing any of these calculations on the computer. And he actually describes how to calculate this thing. But he's not interested in computationally calculating this thing using a computer. He actually wants to calculate this thing by hand. So he talks about how you can take a protractor and actually calculate these cotangents and use that to calculate the Laplacian. And he mentions, well, you better hope these triangles are nice and shaped, because the triangles are very badly shaped and it's very hard to actually measure the angles accurately using the protractor. And this was a problem back when we were using protractors to measure things like the cotangents, but it's still a problem today, because the badly shaped triangle measure and get bad results. We'll talk about that in a bit in a second. So Keenan Crane is actually very passionate about tracking down the history of this thing. So if you look at his thesis, he talks a lot about where the cotangent formula came from. He gives several different derivations of the I'm just going to give you one. I feel like I can't give a lecture on the Laplacian without giving you at least one derivation for where this cotangent formula comes from. So let's look at the cell here in dark blue. And let's say I want to calculate the integral of the Laplacian over this cell. And I'm going to approximate the integral of the Laplacian over the cell in two different ways. The first way I can do it is just to take the Laplacian at the point I, and just assume that the Laplacian is constant over this entire cell. So the integral of the Laplacian over the cell is roughly just the area of this cell times the value of the center. That's going to be my first way of approximating the Laplacian. That's just the area times the value of the vertex. The second way I'm going to do this is I'm going to apply Stokes' theorem. So I'm going to use the fact that the Laplacian is a divergence of the gradient. And now I'm going to apply Stokes' theorem to turn the integral over the interior of a divergence into an integral over the boundary of just the vector field times the normal direction. So I get that the second estimate for this term here is just the integral on the boundary of the normal vector times the gradient. And now I'm going to discretize this on my cell. So let's say I look at one little piece. This thing is dying, unfortunately. Let's look at one little piece of the boundary here. The gradient of u is just going to be the value of u here minus the value of u there, divided by the distance between vertex I and vertex j. Just a finite difference is going to give you the gradient in that direction. And now I just have to integrate that over the length of this piece of the boundary. So you're going to get that this integral here just turns into a difference of u at I and j times some length factor that corresponds to the length of this, the length of that segment down here, divided by a factor that comes from the length of the distance between I and j. And if you crank out some trig, you're going to get that those equal to cotangent. So the cotangents come from the fact that you have these lengths that come from this integration around them. And finally, you get then that the left-hand side, the approximation of the integral over the cell of the Laplacian of u is equal to this formula that has this sum of the cotangents times the difference of u's. And now this is equal to ai times fi, so we get fi just divided by ai. And that's where the 1 over area term comes. That's in front. Now, this formula is very famous. People like to just get some code that has implemented this and code it up and try it on a triangle mesh. And it's very common that you try it and you get very bad answers. You try to apply this to some mesh you download from the internet and you get very bad answers. And the reason for this is that the Laplacian formula is only really good if you have good triangles. What is a good triangle? This is kind of a subjective thing, right? If I show you a triangle and ask you, is this good or not? Maybe it's hard to come up with a rigorous definition of what a good triangle is, although there are some resources that try to do this. But definitely you can look at a triangle and you can tell these are bad triangles, these are good triangles. Right? You want triangles that are not too skinny or the angles are not too small. One kind of good triangle that is well defined is a Delaunay triangle. So if you have a bunch of triangles, the triangulation is the law that you can draw a circle that circumscribes every triangle so that no other vertices are inside the circle. So this here is a Delaunay triangulation, this one is not. And if you have a Delaunay triangulation, then the Laplacian turns out to be very robust. It turns out to be very numerically robust. Whereas if you have a non-Delaunay triangulation, then you can have very large errors in the Laplacian. And so in practice, if you want to use the Laplacian on a triangle mesh, the first thing I always do when someone gives me a triangle mesh is I remesh it using any of many different tools that are available online so that it's a Delaunay triangulation, before I even try to do any calculations on the mesh. Okay, so the cotangent formula is a formula for how to calculate the Laplacian at every vertex. You give me a function u at every vertex, and I can calculate the Laplacian at any given vertex by doing this cotangent formula. And I can write this in matrix form. So here's the code. So let's forget about the area term for now. Let's forget about the A. We'll put the A back in later. Or if we forget about the A, then the Laplacian is just the sum of cotangents. And I now want to write this as a matrix. So that if I do a matrix vector multiplication, if I take my matrix C and I multiply it by a vector that contains all the values of u, I get out a vector that contains the Laplacian of u at every vertex. And what's that going to look like? Well, each row of my matrix is going to correspond to one application of the cotangent formula, right? If I take the row I of my matrix and multiply it by u, that's going to have to give me out the Laplacian at vertex I. So what are the entries of that row going to look like? Well, if I look at the cotangent formula, I can see that for every neighbor, uj of vertex I, I'm going to get a term that has these two cotangents in it. So for every off-diagonal entry of this row, that's a neighbor of vertex I, I'm going to get this sum of cotangents. And then on the diagonal, I'm going to get a whole bunch of terms. So for every neighbor, I'm going to get one term on the diagonal. Do you guys see this? Every term of this sum is going to have something that depends on ui. That's multiplied by ui. And in fact, this diagonal term is just going to be the negative sum of all the off-diagonal terms. So if you want to build this matrix, the easiest way to do it is just to fill in the off-diagonal terms first using these cotangents, and then just take the sum of all the entries in the row and set the diagonal entries to negative that. And everything else is zero. So the Laplacian is local. The Laplacian at a vertex only depends on the neighbors. It doesn't depend on what's happening far away in the place. Does this make sense? Do you think you could code this up if you had to? Yeah, one really key point is that this matrix is sparse. I just said it's sparse, but I feel like I have to say it again. This matrix is sparse. Do not use a dense matrix to represent this. This is like the #1 bug. If someone's working on a project, and someone in my class is trying to implement this thing, and they come to me and say, I get site faults, it runs out of memory. Or this thing is slow, it takes minutes to calculate. First thing I ask is, are you using sparse matrices? So sparse matrices are more complicated than dense matrices. You can't just create a big array of numbers, right? There's lots of libraries that support sparse matrices. MATLAB is really easy to support sparse matrices. And Eigen's the C library that I really like to use for linear algebra. It has nice support for sparse matrices too. It makes a huge difference. And if you have a huge mesh, every row of the Laplacian is only going to have 7 or so entries that are non-zero. All the other entries are going to be zero. You don't want to have to store all those zeros in memory. It's going to kill you. Okay, so a second ago I ignored the A's that were out in front of the cotangent formula. What do I have to do if I want to put these back in? If I've got a matrix that encodes every part of this except for the 1/A, how do I make a matrix that also has that 1/A term? Yeah, that's right. So I just want to scale row 1 by 1/A1, scale row 2 by 1/A2, and so forth, right? So what I can do is I can create a matrix M, which just has all the A's along the diagonal. And then I multiply my matrix by the inverse of this thing. So yeah, so this thing just has the A's on the diagonal, everything else is 0, and then M inverse times C just rescales all the rows by 1/the A's. Now that gives you the final formula for the Laplacian. Does that make sense? And you can work out, just as a sanity check, if you take this L and you multiply by some vector of u of all the values of u on the vertices, you get out exactly the cotangent formula. Multiplying by c and then multiplying by inverse just evaluates the cotangent formula at all of the vertices. Now, if I want to solve something like the Poisson equation, Laplace u equals f, what do I do? Well, my f here now is an f that's at every vertex. And I now want to solve a linear system. I have my matrix L, I have my unknown vector u, that's my solution to my Poisson equation. I just have to solve a linear system, L u equals f, to get the value of uf. And you can prove that if you have a nice mesh, if you have a Delaunay mesh, or a mesh that's not too badly triangulated, you refine it. And look at the solution you get in the limit of refinement, that your solution to the Poisson equation is going to converge. So if you have a fine enough mesh, you can have a good approximation to what the Poisson equation actually would be on a smooth surface, on a smooth body, or on a smooth whatever you want. If you want to solve the Laplace equation, if you just want a 0 here instead of an f, that's just a special case, right? There's nothing extra special there. You just put it in 0. Now, let's say you wanted to solve the heat equation as an ODE. So let's say that you want to implement this formula using a discrete mesh. How do you do it? Well, we know how to discretize the right-hand side. We know how to write this as a matrix times a vector. All we need to do now is discretize the left-hand side, the time derivative of u. Well, the way to discretize the time derivative is a finite difference. So I'm going to have a function u for every step in time. And the time derivative of u is going to be u at time k plus 1 minus u times k over the difference in time between time k and k plus 1. Now, I need to approximate this right-hand side. I know how to approximate the Laplacian. I have a matrix L that encodes this. But what do I use for u? I could use u at time k, or I could use u at time k plus 1. Or I could use u at the average of the two times. So I could cook up any number of schemes for what u to approximate on the right-hand side. The easiest thing to do is just to take this u and say that it's uk. It's u at time k. If I do this, I get a very easy formula to solve. If I want to solve for uk plus 1 here, all I have to do is move this stuff to the right-hand side, and I have my solution. Right? It turns out if you do this, it's not very stable. If you have an h that's too large, you blow it. It's much more stable to take u and discretize at time k plus 1. How would you solve this thing then? So you know u at time k, you want to solve for u at time k plus 1. How do you do it? That's right. So I need to turn this into a linear system involving uk plus 1, right? So I'll subtract, or I'll move these two uk plus 1 terms to the same side, and I get something that looks like this. So I've got some matrix here. It's no longer just the Laplacian. It's I minus h times the Laplacian. It's my matrix here. uk plus 1 equals uk. Now I solve this. Can anyone see why this is more stable? Why is this stable, this solve here?
Does it have a division? Does it have a division, or everything is multiplication?
Everything is multiplication. Well, I mean, it kind of has a division, right? You're dividing by the matrix when you solve a linear system, right? But the division that you're doing by this matrix, the linear system that you're solving here is a very robust one because this matrix here is positive definite. The Laplacian is negative definite, and multiplied by minus and add the identity to it, it gets something positive definite. And for that reason, solving this thing is very stable, even if h is very large. You don't have restrictions on the size of h the same way that you do if you try to solve the system. So for that reason, in practice, people like to do the second approach because it does give you very stable steps. Now, what if I want to solve the eigenvalue problem? Well, that just becomes a discrete eigenvalue problem. I have my matrix L that represents my hypothesis, and I want to find a vector U, which represents my eigenfunction, so that LU equals lambda U. And there's several techniques for how to solve this. Usually you just use a black box method that calculates eigenvalues. There's a very popular method called power iteration. You basically just hit the matrix over and over again, or hit a vector over and over again by the matrix. I think, did Justin talk about this? Someone talked about this yesterday, so I'm not going to go too much detail into it. There's several standard techniques for how you can extract eigenvectors and eigenvalues from a matrix that you can use to find eigenfunctions that will discrete. Okay, so I talked a bit about the properties of the smooth Laplacian. I'm going to talk a bit about how these generalize or how these apply to the smooth Laplacian. The first is just like the smooth Laplacian, if you did f Laplace f and integrated that up, you always got something negative. Because this is just the negative of the Dirichlet energy, so it has to be negative. It's also true that if you have the cotan Laplacian, you always get that it's negative then. Doesn't matter how bad the mesh is, it's always negative then. The reason for this is that, again, if you look at how we derived the Laplacian, we derived it from the Dirichlet energy. And so we get that if you calculate this, you're basically calculating a discrete Dirichlet energy and taking the negative of that, and that has to be negative for the same reason that the smooth Dirichlet energy has to be negative. So the integral will bunch over to a positive things. Just like a constant function is in the kernel of the smooth Laplacian, if you have a vector that's all constant values, and you hit that with the Laplacian, you're going to get 0. Why is that? Why do you get that the Laplacian with constant vectors? Yeah, when you built this matrix, you set the diagonal to be negative sum of the other entries of the row, right? So if you multiply this row by any constant vector, you're always going to get 0. Just from the way you built the matrix, it's built in that if you hit it by a constant vector, you get 0. Okay, and this is important because you have a matrix and it's not a full rank matrix, right? The matrix has a kernel, and you have to take that into account when you want to solve linear systems, right? If you're trying to solve a Poisson equation, then you have to make sure that the right-hand side of the Poisson equation is valid. Will have a solution. If it has a component of the constant vector on the right-hand side, and you try to solve it, your solver is going to give you an error. It's not going to work because there doesn't exist a solution for this. It also means that if you have a Poisson equation, you've always got a constant to the solution, you'll still get a solution. Right? So the solution is not unique. It's only unique after adding a constant function to the solution. Just like there's a maximum principle. So just like if you solve the Laplace equation in the smooth case, or if you have a harmonic function in the smooth case, then you're only going to have critical points at the boundary. This is also true if you do the same thing in the discrete case. If you solve a Laplace equation in the discrete case, if you have a discrete harmonic function, you're always going to get the maxima on the boundary if the mesh is below. If you have a more general ugly mesh, it's no longer guaranteed that you have a maximum principle. And this is very bad because you can have arbitrary bumps in your function that's supposed to be smooth. And if you're using the Laplacian for doing things like deformations, right? You tend to get things like inverted triangles, you tend to get very bad deformations, but you can't guarantee the fact that you have a maximum principle. You can have injectivity, all kinds of problems. So this is another reason you really prefer Delaunay mesh for doing these operations. Using a Delaunay mesh guarantees nice properties, like the fact that you have a maximum principle. Yeah, and people don't really know. So even if you have a mesh that's not Delaunay, you can get lucky. Actually, oftentimes you do get lucky. You have a maximum principle, even though you have an ugly mesh. But it's really not very well understood when you have a maximum principle and when you don't. There's no good geometric characterization of when you have one and when you don't. This is still an active area of research. Okay, if you actually want to solve a linear system involving this Laplacian, this is very easy to do because this Laplacian is kind of the best thing you can have for solving linear systems. It's a negative semi-definite matrix. And there's lots of specialized algorithms that will work with these matrices. Many algorithms actually want positive definite matrices, so it's very easy just to multiply the Laplacian by -1, or multiply both sides by -1, and you have a positive definite matrix. And you can use things like Cholesky factorization, or you can use the method of conjugate gradients, or you can use all these specialized methods that will work for symmetric semi-definite matrices. Yeah. Now, one thing that's a little annoying is you have this M inverse term that appears here. So if you have the M inverse term, this kind of breaks the symmetry of the matrix, right? So the matrix C here is symmetric, but once you multiply by M inverse, it's not. But in practice, it's not a problem, so you can always move the M particle talking to the other side. So you can take M inverse times C equals U equals F and move the M to the other side. This M is a diagonal matrix, so it's very easy to move it back and forth if you want to. And now you get something that looks like positive definite matrix times U equals right hand side. And now you can solve this again using cholesterol factorization, or whatever your favorite solver is. Yeah. But it makes a big difference. If you've ever used linear solvers before, if you have a general linear solver like LU decomposition, this turns out to be a lot slower and less robust than Cholesky factorization. So anytime you can get away with rearranging your equations so that you get rid of the M inverse, so that you get something that's symmetric, it's always worth it. So same thing here. If you have the heat equation, you want to solve this thing here. Instead of having I minus LH UK plus 1 equals UK, you multiply everything by M. And now this again is a symmetric matrix. M is symmetric and C is symmetric. And you can solve this instead of I minus HM. Same thing with the eigenvalue problem. If you have an eigenvalue problem and your L matrix is not symmetric, you can make it into something called a generalized eigenvalue problem and multiply both sides by n. So a generalized eigenvalue problem is like an eigenvalue problem. It has two matrices. It has one on the left and one on the right. And most numerical packages that can solve eigenvalue problems can also solve these generalized eigenvalue problems. And so you use this to calculate eigenvalues instead. If you don't have support for generalized eigenvalue problems, you can also use this trick. We multiply the matrix on both sides by the negative square root of n. And that turns the matrix into something symmetric. You solve the eigenvalues of this, then you multiply again by this negative square root of n to get back the eigenvalues of the original matrix. And square roots of arbitrary matrices are kind of not well posed, but if you have something that's positive definite, like the mass matrix, or the matrix of areas, you just take the square root of all the diagonal entries. And that gives you the square root of the n matrix. Okay, in terms of solvers, there's really two approaches that you can take to solving linear systems. This approach is called direct solvers, which you basically give it the matrix and it gives you out the answer, and it just performs a calculation. And when it's done with the calculation, you have the answer. You don't have any intermediate results. You just have the answer. Things like Cholesky decomposition or LU decomposition are some examples of direct solvers. And the advantage of this, the direct solver, is that they tend to be very fast. And they tend to give you factorizations of matrices. So if you have to solve a lot of linear systems that have the same matrix but a different right-hand side, you can compute the factorization once, then reuse it to solve lots of linear systems. So if you have some buddy, and you want to solve the Poisson equation many times with different right-hand sides, then you want to use a direct solver, so you can pre-compute what the factorization of the Laplacian is. Yeah, the problem is they tend to not scale very well to large matrices, and they really are all or nothing. If you get back your answer from a direct solver and it has large error, there's not much you can do about it. It's not like the other approach called iterative solvers, where you can keep running the solver for more iterations, getting more and more accurate results. So methods like conjugate gradients are examples of iterative solvers. Multigrid is an iterative solver for very, very, very large problems. So people that do fluid simulations. I've got a friend at Harvard who's doing a fluid simulation of how fish swims, and it's been running for the past 3 years. I keep telling him, I really hope this code's not buggy, because if it comes out after 3 years and it's totally wrong, then you're going to waste a lot of time. But he's trying to solve this really, really huge Poisson equation. If you're running fluid dynamics, there's this pressure projection step that you have to do that turns out to end up having to solve a linear system one more question. And specialized solvers called multigrid solvers can really, really quickly solve these really, really huge equations in one-to-one fashion. So these tend to scale very well. The problem is they don't give you decomposition like direct solvers do. So if you have to solve the same problem many, many times over again, sometimes it's worth just using a direct solver instead of having to solve the same problem over and over again to do it. And there's no really one size fits all. It all depends on what you want to do with the equation you're trying to solve, which is the best solver. Okay. I guess I'll mention one thing before we end, with a few minutes left, is that the boundary conditions for the Laplacian can be true. I've kind of ignored the boundary conditions in the talk so far, but they're very important, they're very easy to get wrong, and they're kind of hard to find in the literature. It's hard to find what exactly to do for the right boundary conditions if you try to look up the Poisson formula for the Laplacian. So like I mentioned before, there's two kinds of common boundary conditions. There's Dirichlet boundary conditions, where you basically prescribe the value of a function on the boundary and try to solve Laplace equals 0 on the inside, subject to the boundary values being what they are. And there's the Neumann boundary conditions, boundary conditions where the derivative in the direction of the boundary is 0. If you want Dirichlet boundary conditions for the discrete Laplacian, what you do is you basically segregate your vertices. So the vertices that are on the inside and vertices that are on the boundary. And then you look at your matrix C, and you split this matrix C into blocks. We have one block that's for the one set of blocks that's for the interior vertices, and one set of blocks that's for the boundary vertices. And the boundary vertices are not allowed to change. The boundary vertices are just whatever the values are that are prescribed in the Dirichlet boundary conditions. The only values that are allowed to change are the ones in the interior. So these values UB you already know. These things you're not allowed to change. The only values you're allowed to change are the values UY. So what you can do is you can go ahead and plug in the values you know for UB. And then you can rearrange this matrix so you're only solving for the part that you don't know, the UI. So basically the term that you get, if you multiply this block row here by this vector here, you're going to get CII times UI plus CIB times UB. And the CIB times UB you already know, so you already know what the UB has to be on the boundary. And you can rearrange your equation now so you're only solving for the UI. So this part here is just moved over to the right-hand side. And you solve this smaller set of linear equations to get what the values are on each. If you have Neumann boundary conditions, it's a bit more tricky. You have to go back to the derivation of the Laplacian for the Neumann case. So now what you get is you get that when you integrate over this dark blue region here, you still get the same terms for the edges that are interior. But for the two boundary edges, you have a shorter boundary. You have a boundary that's only half length long. And now you also have an extra part of the boundary that didn't appear before, which is the part that's on the mesh boundary up here. And you have to, so basically you have to modify your cotangent formula for this boundary vertex I to take into account the fact that the term that corresponds to these two pieces here are half as big as they used to be, and you also have an extra term for the top two pieces. The easiest case to deal with is the case where your Neumann conditions are 0, where you just have that the normal drift has to be 0 everywhere, the natural boundary conditions. And here you can kind of just pretend that the vertices are not boundary vertices. You can just use the cotangent formula naively, and you'll get the right answer. But if you want your derivative to be anything else other than 0, then you have to really go back to this derivation. Make sure you put in the right terms for the cotangent formula on the boundary vertices. Okay. And like I said before, I've talked about triangle meshes, but with what you know about how the Laplacian is defined in terms of Dirichlet energy, you should be able to also apply this thing to other domains. So for example, point clouds are very popular right now because if you have a connect or any kind of other depth sensor, it's very easy to scan in point clouds. And you can define a Dirichlet energy on a point cloud pretty easily. If you have a function that's defined with a bunch of scattered points, you can calculate a gradient at a point just by looking at nearest neighbors and saying, how's my function changing as I move from myself to my nearest neighbors? And once you can define a Dirichlet energy, you can define a Laplacian. You can apply all the stuff we talked about today to the setting. You can also do the same thing with your tetrahedra. You can define a variation of the cotangent formula for tetrahedra. You can do the same thing with quads, all kinds of other settings. All right, so any questions about the Laplacian?
Why might you not care about the area? Why would you use an unrelated version?
No, so you do care about the area. So actually, sometimes people don't care about it, right? If you talk to people that try to do things like graph embeddings or something like that, people tend to write down Laplacians that only look at connectivity information and don't talk about distances. This sometimes makes sense for any kind of geometric application that you do in computer graphics. You will care about the weights. Yeah. You do care about the sizes. When I say don't worry about the weights, I mean don't worry about them for now. So all the weights do appear in the M-inverse matrix. And you move that matrix to the right-hand side, but it's still there. The solution that you get by solving L or CU equals MF, right, is exactly the same as you get by solving LU equals L. It's just numerically a lot more robust.
Yeah, it was more about the construction of
Oh yeah, so for the construction, I first built the matrix C, and then I built the matrix M, and I made L equals M inverse C. And once you have M inverse C, then the weights are picking. Yeah?
well, so at the very start, you ignored the case where you had you said we couldn't have a measure with intersecting bases.
Oh, if you had a T-junction in your mesh, or what do you mean by intersecting?
Well, yeah, so you said we couldn't have things.
Yeah, yeah.
And is it, can we not have it because it's too difficult to see, or can we not have it because it's too hard to look at?
There must be a way, yeah. So if you have a simplicial complex that has things like non-manifold edges, there must be a way to just, there must be, right? Because you can still write down a inertial energy on this thing. You don't really need an orientation to do that, right? I'm not sure offhand how this looks. Does anyone else know, like Alec, do you know?
Yeah, so if you just naively implement the cosine Poisson on a non-manifold mesh, it turns out to be the same as if you implemented it on each manifold patch and then glued it together with constraints saying on the manifold edge, the values must be the same.
And that works well.
Well, it's a reasonable thing to do, I guess. You sort of say, like, you have two nice surfaces and they're constrained to be the same on the parts that they do that.
Other questions? Yeah.
So if you look at the overall Laplacian cotangent formula, so supposing if I have a mesh with, let's say, 100,000 vertices, and let's say I have the same mesh like the bunny with 10,000 vertices, and apply the cotangent formula, it appears that the Laplacian spectrum will be different for these two because of the cotangent formula. Is that right? Or?
They will be different. So let's say you take a discrete sphere, and you look at the spectrum on the discrete sphere. So you know that the smooth sphere has infinitely many eigenvalues, and you know what they are. They're the spherical harmonic eigenvalues, right? If you look at the discrete eigenvalues, you'll see that the first few are very, very accurate. And the accuracy really drops off as you go to higher frequencies. And that's because the very high frequency eigenfunctions are just encoding the noise in the triangulation, and not the actual geometry of the sphere. So if you plot the spectrum, you'll actually see that they start to diverge quite badly. So if you look at the sphere spectrum, maybe it looks like this. And if you look at the discrete sphere spectrum, maybe it looks something like that. And if you have a higher resolution sphere, you're going to get more accurate, right? So you're going to have more of your eigenvalues are accurate for longer than if you have a coarser version. So absolutely, you won't get the same, but the low eigenvalues will be more or less the same. Because those are actually faithfully encoding information about the geometry, not about the discretization. Other question, yeah?
So instead of using a cotangent formula, is there other formula like the geodesic function or distance between the vertices? Those can be encoded into the Laplacian.
So you're saying you want to use geodesic distance instead of the distance of the edges? Well, so if you somehow know that, you could do that, right? If you have some other metric that you use other than Euclidean metric, that should be fine. I mean, you also have these area terms, right? You have to have some way of calculating the areas. If you have some geodesic area, somehow you have to calculate this, right? But if you have this, then sure, you can use that. Other questions? All right, let's go to the coffee break.